Okay. In this case, we're now going to consider forced response, where we'll have forcing applied to both of the modes. In this case, we're going to have all the previous terms that we had before. So we'll have a damping 2 C1 hat times U1 dot plus alpha 1 U1 cubed plus alpha 2 U1 squared U2 plus alpha 3 U1 U2 squared plus alpha 4 U2 cubed, and then lastly plus, we're going to have a force here F1 times the cosine of omega t plus some shifting tau 1. Second mode, we're going to have minus 2c2 hat u2 dot plus alpha 5 u1 cubed plus alpha 6 u1 squared u2 plus alpha 7 u1 u2 squared plus alpha 8 u2 cubed. Okay, so the nonlinearity and the damping here are strong, which means we'll end up having, depending on what we do, we will have to seek solutions starting at order epsilon 1. And we will also do some scaling based on the type of case that we're interested in, the type of resonance we want to study. So we're going to start by considering primary resonance, just like we did before. So the forcing is close to one of the natural frequencies of the system. And in this case, we're also going to assume that omega 2 is larger than omega 1, and they're distinct in this case. And for primary resonance, we're going to rescale the damping to be weak, meaning that C1 hat, C2 hat are equal to epsilon squared C1 or epsilon squared C2. And then we're also going to scale our forcing, and this time we're going to go take it down to epsilon cubed times lowercase fi. From here, so the reason we're going to rescale this is that we want the damping and the forcing to appear at the same time scale. And what you'll find in this expansion is that order epsilon 2 is the same as order epsilon 1, which means that it doesn't introduce anything interesting, which means that like x1 solves the x2 equation, so x1 and x2 are equal to each other. And therefore, we skip from x1 and just study x3 as a result of that. Okay, so we're going to do an expansion just like we did previously. We're going to expand, into specific orders as shown here. And we're going to consider two timescales, T0, T2, and all the nonlinearities are going to appear at order epsilon 3, and that tells us that the ODE for order epsilon 2 is the same as the ODE for order epsilon 1, such that U2 is equal to U1, which should be like U21, 1, 1 or something like that. Yeah, I left out a 1 here. I did not mean these U's up here. These are not equal to each other. It's that this term is equal to the second one. Okay. At order epsilon, we end up with two equations. We have D0 squared U11 plus omega 1 squared U11 equal to 0. And our second equation, we have D0 squared U21 plus omega 2 squared U21 equal to 0. We can solve both of these directly. From the first equation, we'll get that U11 is equal to A1 function of T2 times e to the j omega 1 T0 plus its complex conjugate. From the second equation, we'll get that u21 is equal to a2 function of t2 times e to the j omega 2 t0 plus its complex conjugate. All right, we're going to write out the equations at order epsilon cubed, and we won't substitute in the solutions for u11 or u21 yet. That's on the next page, and I've left that in. But at order epsilon, the equation we get here is minus 2 d0 times d2 u11 plus c1 u11 dot actually, I think that dot should not be there, because the dot should represent, yeah, d0, which we've already pulled out. Yeah. Yeah, it should not be there. So it should just be c1 u11 plus alpha 1 u11 cubed plus alpha 2 u11 squared u21 plus alpha 3 u11 u21 squared plus alpha 4 u21 cubed plus lowercase f1 times the cosine of omega t0 plus tau 1. For our second equation, we're going to end up with minus 2 d0 times the quantity 1 d2 u21 plus c2 u21 plus alpha 5 u11 cubed plus alpha 6 u11 squared times u21 plus alpha 7 u11 times u21 squared plus alpha 8 times u21 cubed plus lowercase f2 times the cosine of capital omega t0 plus tau 2. All right, I'll give you guys a chance to catch up. All right, so if we substitute in our solutions for u1 and u21, we end up with the following terms shown here. I'm just going to circle first our obvious secular terms. Right here, again, obvious secular terms. Then we also have potentially secular terms, which I'm going to circle first one in orange here. We also have another term that is potentially secular down here. And then one last term at the bottom. And this time, that external forcing we're including in our potentially secular terms. Second equation, we again will have an obvious secular term here. And then we'll have three different potentially secular terms. First one here, I'm going to circle in orange. The second potentially secular term is right here. And then lastly, this term in purple is potentially secular. Okay, so these terms, except for that forcing, all of them are the same as what we saw previously. So really what we've added here is this forcing term. So in the absence of internal resonances, the steady state motions are going to be uncoupled, and if you want to study that, you can do what we did previously for a single degree of freedom system, meaning that we are not going to do that in class. We're going to skip ahead and study something more interesting. In this case, we're going to study this 3-to-1 resonance that we observed previously without the forcing. That's just due to the fact that the nonlinearity here is cubic, so it gives rise to this 3-to-1 internal resonance. And based on that, we're going to introduce the following detuning. And here we're going to use a sigma 1, and we'll end up with a sigma 2 in a moment. We're going to say here that omega 2 is equal to 3 omega 1 plus epsilon squared sigma 1. Put epsilon squared in there so that we'll end up with a, we'll end up with T2 rather than T1 because we're considering here in our expansion, we expanded to T0, we skipped T1, and we included T2.
Excuse me?
Yeah.
Just before we move forward. So here when you're choosing the potential signal terms, do you look at both equations or just one equation?
So
For example, the green one and the
Yeah.
second and the third 3b. So when you say omega 2 minus 2 omega 1, and we made an assumption that omega 2 is bigger than omega 1.
Yeah.
So how can we get a circular term in this case?
So the green term specifically, but it applies elsewhere. So if we have here, we have this relationship omega 2 minus 2 omega 1.
Yes.
So
For this one, yeah, makes sense.
right.
I'm talking about the 3b, where we have omega 2 minus 2 omega 1. How in this case could we get an omega 2?
Mm-hmm. Yeah, I get what you're saying. So give me a second. So, it's a good question. It's actually, that particular one is actually in the complex conjugate right now. That's where it is. So in there, we will have something like, okay, I'll expand this separately and point it out. And I've looked at, not this one, but I've done it for the homework problem. And I've checked all the different resonances. So you're right. This term right here is not potentially secular, but there is a mirroring term in the complex conjugate, which I'll have to go outside of class and pull that up and answer that question. But yeah, you raise a good point, and I agree with that analysis. Okay. So that being said, let's just go with our assumption that there's some secular term in the CC that will pop out and we'll have to deal with. And I'll also say that in the next set of equations that we're going to write down, this term right here does not actually appear. It's a term that I can't find here. Hold on. So actually, that term becomes secular. Okay.
I think you found something reasonable.
So I was saying, like, if we try to rewrite that expression into two exponential terms, right? Each one of the frequencies is
We're talking about this term?
yeah. If you like make it e exponential omega 2 multiplied by e exponential 2 times omega 1 t naught, the individual exponentials are approaching the omega 2. So it's, even if you look at only one of it out of the expression, it's almost clear, which you can assume is separate. That's what I was saying.
So what you, so I don't think this is a secular term.
Oh. Unless if we are, so I think this could be a secular term just in one case.
Yeah.
If we don't look at these equations as separate equations. So this could be a secular term, but affecting the first equation, maybe the other mode.
Well, no, I disagree with that. I would actually say that this term that I've circled, this term right here, that one's actually secular, because it's got the 3j omega 1 in here, which you, omega 2 minus sigma t2, and, well, sigma epsilon squared. So what needs to happen is I need to go back and double check my notes, and the notes when I originally took a class based on this stuff, and double check these secular terms, because I think somewhere I've circled the wrong terms in the second equation, because this should not be a secular, oops. Unless, unless, for example, I know, you can invent some ratio where that makes sense, but that doesn't mean it makes physical sense. Like, you can invent a mathematical relationship where this equation becomes, this term becomes secular, but that doesn't mean that that makes physical sense. or satisfies the assumptions we've made about omega 2 and omega 1. You know, if omega 2 was like negative, for example, yeah, right. I mean, you could make it work, but that doesn't really have any physical meaning. So let's just, the obvious secular term is fine.
Yes.
And we will ignore the orange and purple terms, and then I'll get back to you guys next class
And,
with this.
yes, and the orange one is also, like,
Yeah.
so it's because just based on the assumption.
Right.
It's like
So,
times two omega
so it
plus
should
omega.
be, you know, we ignore this term, and well, okay, the fourth thing is potentially, but ignore this one over here for now, and then I'll revise the notes and give you guys like a new page for it. Okay.
So anyway, is when thinking about this, we can get some seculars in one of the modes and not in the
You
other
get
mode?
different secular terms in each equation, because what you're looking for in this first equation, we're looking for terms that have e j omega 1 t0, because that's the natural frequency of this guy. So that would be forcing at the resonance of this equation. In the second one, we have omega 2, so we want anything e to the j omega 2 t0. That will be then forcing at the resonance of this equation. That's what we're looking for, and that's what Mohammed pointed out here, was that this term right here can't give you a secular term because, well, if we just go with omega 2 being 3 omega 1, you get omega 1 here, which is not going to resonate with the natural frequency. So it can't be a secular term. It's just some forcing at that point. And which then led me to say, well, hold on, if we come here and we we say that omega 2 is equal to 3 omega 1, we can then make the substitution, and here we'll get forcing in omega 2. And the same thing is, here we have omega 1t, which in this case, this is the one-to-one resonance term, which we're not studying, but you could study in certain cases. Over here, this term here is probably not secular, right? And instead, may or may not be another term that accounts for it. So what we'll do here is we will lasso this, move it over, and the forcing term can still be secular. Okay. Are there any other questions before we move on?
Beside the purple term, you said that can't be secular, right?
Can you repeat that?
Beside that purple, what is purple? You said that term beside it is not secular?
Here?
Yeah.
Yeah, it should not be secular.
What if omega 1 is 3 omega 2?
I think it's non-secular just because of the assumption we made at the beginning, which is omega 2
Yeah.
greater than omega 1.
Oh,
Otherwise,
yeah.
all of these could work.
Yeah. And like I said, if you wanted to study negative frequencies, which doesn't make any physical sense, you could then come and do stuff like this. But yeah, in that case, it's not secular because we've assumed that omega 2 is always greater than omega 1. If we had not assumed that, then this could be. Yeah. Okay. The first thing we're going to consider here is we're going to consider two cases, one where the forcing is at omega 1, and then another where the forcing is at omega 2. We're going to start with the forcing at omega 1, so we are forcing the system at the first frequency of the first mode. And we introduce a second detuning parameter sigma such that capital omega is equal to lowercase omega 1 plus epsilon squared sigma 2. We substitute that in, we're going to end up with the following two equations. First, we'll have minus 2j omega 1 times the quantity big A prime plus C1 times A1 plus 3 alpha 1 times A1 squared, A1 over bar, plus 2 alpha 3, A2, A2 over bar, times A1, plus alpha 2, A2, A1 over bar squared, times E to the J, sigma 1, T2, plus 1/2 F1 times E to the J times the quantity, sigma 2, T2, plus tau 1. And that's all equal to 0. And then in our second equation, we will get minus 2j omega 2 times A2 prime plus C1 A2 plus alpha 5 A1 cubed e to the minus j sigma 1 T2 plus 3 alpha 8 times A2 squared A2 over bar plus 2 alpha 6 A1 times A1 over bar times A2, and that's all equal to 0, and there's no forcing in the second equation because we are forcing at omega 1.
And that second equation should be C2, A2?
Yeah, it should be C2. Okay, we're going to just introduce polar notation, just like we have done many times before. We're then going to plug those in and collect real and imaginary terms, separate them, set them each equal to 0, and then we'll get the following 4 equations in this case. First, we'll get 8 omega 1 times A1 prime plus C1 A1. This is then equal to alpha 2 times A1 squared A2 sine gamma 1 plus 4 F1 times the sine of gamma 2. And then our second equation is 8 omega 2 times A2 prime plus C2 A2 equal to minus alpha 5 A1 cubed sine gamma 1, and then 8 omega 1 A1 B1 prime equal to minus 3 alpha 1 A1 squared plus 2 alpha 6 A1 squared. All of that multiplied by A2 minus alpha 2 A1 squared A2 times the cosine of gamma 1 minus 4 F1 cosine gamma 2. We got one more equation. Let me try it. We got one more equation, which is 8 omega 2 A2 B2 prime. This is then equal to the quantity minus the quantity 3 alpha 8 A2 squared plus 2 alpha 6. All right, hold on. In the equation 37C, this term that I just erased, and then I'll just put the laser right here. This term right here, that term is actually 2 alpha 3 times A2 squared. And the one beneath it is 2 alpha 6 times A1 squared. All of that multiplied by A2. And then also one more correction on 37C. This term that I just circled with the laser, that should be A1, not A2. Again, that term right there should be A1. Okay, going back to 37D, we'll have last term is minus alpha 5 A1 cubed cosine gamma 1, where the two gammas are defined as follows. All right, so under steady state, whoops. Okay, so under steady state, we're again going to set all of the A primes and all of the gamma primes, or this should say B prime. All of the B, I primes, those should be equal to 0. And that leads to the following equations, that 8 omega 1 times C1 A1 minus alpha 2 A1 squared A2 times the sine of gamma 1 minus 4 F1 times the sine of gamma 2 is equal to 0. Then the second equation is 8 omega 2 times C2 A2 plus alpha 5 times A1 cubed times the sine of gamma 1, and that's equal to 0. The third equation is 8 omega 1 times A1 sigma 2 plus quantity 3 alpha 1 A1 squared plus 2 alpha 3 A2 squared. All of that multiplied by A1 plus the quantity alpha 2 A1 squared A2 times the cosine of gamma 1 plus 4 F1 times the cosine gamma 2, and that's all equal to 0. And then we have one more equation, which is 8 omega 2 times A2 times 3 sigma 2 minus sigma 1 plus quantity quantity 3 alpha 8 times A2 squared plus 2 alpha 6 times A1 squared, all of that multiplied by A2 plus alpha 5 times A1 cubed times the cosine of gamma 1, that's all equal to 0. Okay, so these 4 equations can be solved numerically. We're just going to look at the results produced by Nafi, Mook, and Sridhar. I tried to do this in MATLAB, it didn't work, and then I just used their results. So I'm not necessarily sure how they managed to do it. When I tried to do it, it was not solvable, or it gave responses that didn't make sense. In any case, they applied this method to study the behavior of a hinge clamped beam. They decomposed it into 2 modes that were nonlinearly coupled, applied this method to multiple scales, and then solved these equations numerically, which then ends up producing, I have to zoom out here. In this case, this is the amplitude A1 as a function of sigma 2. And this looks very much like what we've seen previously for a single degree of freedom system that was forced, in the sense that we have, at some portions we end up with multiple solutions, some of which are unstable, and therefore you can get this kind of jump phenomena in the second mode here as well, or in the first mode shown here. If we take a look at the second mode, we again get this similar type of behavior, although the curvature here is different than over here. One thing to note is that when we're forcing at the first mode directly here, its amplitude is very large, as you would expect, but the amplitude of the second mode is actually small, relatively small, even though there is an internal resonance here. And so what this tells us is that when you excite the fundamental mode for weak nonlinearity, you will not end up producing strong responses in the higher modes, even though they can be coupled through these internal resonances. All right. That being said, we're now going to take a look at what happens when we force near omega 2 instead. So in this case, we're directly forcing the second mode, and we're going to do the same type of analysis, and then we'll take a look at the results that Nafi and his collaborators came up with. So first, we're going to say here that sigma, or capital omega, is equal to omega 2 plus epsilon squared times sigma 2. And one thing you should know that we're using the same definition for sigma 1 that we did before, or equation 34. We're now going to let f1 equal to 0. I think I forgot to mention this. In the previous analysis, we let f2 equal 0, so there was no forcing applied to that mode. In this case, we're going to let f1 equal to 0 and assume that f2 is not equal to 0. So then results in the following two equations. First, we'll get minus 2j omega 1 times the quantity a1 prime plus c1 a1 plus 3 alpha 1 a1 squared a1 over bar plus 2 alpha 3 times a1 a2 over bar plus alpha 2 a2 a1 over bar squared times e to the j sigma 1 t2. All of that's equal to 0. And our second equation is minus 2j omega 2 times a2 prime plus c2 a2 plus 3 alpha 8 a2 squared times a2 over bar plus 2 alpha 6 a2 a1 over bar. Then plus alpha 5 times a1 cubed times e to the minus j sigma 1 t2 plus 1 over 2 times f2 in this case times e to the j sigma 2 t2 plus tau 2. And that j is multiply this whole thing. And that is equal to 0. All right, we got 4 more equations, and then we'll be done writing equations in this chapter. And then we'll be done with multiple scales as well. And the rest of the writing should not be as much, not as tedious, at least. Okay, so we're going to introduce polar notation, just like we've always done. We're going to then separate into real and imaginary parts, and then we're going to obtain the following 4 equations that govern the slow flow dynamics, which are 8 times omega 1 times a prime plus c1, that should be a1, c1 times a1 minus alpha 2 a2 a1 squared times the sine of gamma 1, and that's all equal to 0. Then we'll get 8 omega 1 a1 b1 prime plus 3 alpha 1 a1 cubed plus 2 alpha 3 a1 a2 squared plus alpha 2 a2 a1 squared times the cosine of gamma 1 is equal to 0. And then we're going to have 8 times omega 2 times a2 prime plus c2 a2 plus alpha 5 times a1 cubed times the sine of gamma 1 minus 4 f2 sine gamma 2, that's all equal to 0. And then we'll have 8 times omega 2 times a2 b2 prime plus 3 alpha 8 times a2 cubed plus 2 alpha 6 times a2 a1 squared plus alpha 5 a1 cubed times the cosine of gamma 1 plus 4 f2 times the cosine of gamma 2, and that is equal to 0. And gamma 1 and gamma 2 are just shown there. All right, so just like normal for steady state, we would set the derivatives equal to 0. We're not going to write that out, but you set them equal to 0, and then you end up with 4 coupled algebraic equations that you can then solve numerically in this case. I'll show the plots actually right now. Again, taking from Nafee and Mook's book and their work. This is the amplitude of A1 in this case. No, I'm sorry. This plot actually shows the amplitude of both modes at the same time. So this curve right here, that is the amplitude of A2, provided that the amplitude of mode 1 is 0. So in this case, you can have a 0 amplitude in mode 1 and then a non-zero amplitude in mode 2. Unlike the previous case where both modes had some non-zero amplitude. Unlike the previous case though, when A1 is non-zero, it will end up being very large. And that's what these curves right here show. So this is the response of the second mode when A1 is not equal to 0, and you can see that A1 is much, much larger. And actually the curves are more complicated than you see here. For this solution case right here where A1 is not equal to 0, these are the stable solutions, but they end up being a bunch more solutions that are unstable as shown here. And so, you end up with this being our stable response for A2, this here being the stable response for A1, and then all of these other curves are unstable.